The afternoon session will be given by Gabriel Ferrari from the University of Trento. And his talk title will be Spontaneous Creation, Dynamics and Interaction Vortices. Right. Okay, thank you for the introduction, and I'd like to thank the organizer for putting together this excellent workshop. And it's very exciting, and I'm very happy to have the opportunity to present the data from the University of Trento and the DC Center. Okay, so here you have some images, nice images that I will discuss later on. These are pictures of our vortices, and this is an overall picture of a film of the dynamics of interacting vortices. Let me first introduce where we are. We are from Trento, which is a small town in the center of the Italian Alps. The work I will be presenting is a joint effort from my experimental work group, and the main people involved were Carmelo Morini, Serafino Togliani, Giacomo Lamporesi. We benefit, of course, from the theoretical team in Trento, led by Franco Dal Fogo and Zlatan Tajewski, Russell Biseto and Fabrizio Latte, also contributed. And also we benefit from the support of our friend at the University of Newcastle. Luca and Carlo Barenghi did a substantial part of the simulation that I will be presenting. So I think that there is no need now to further introduce the general context of interacting vortices. This one, we already have very nice theoretical introductions. And so we go straight to the point, spending a few more words about the platform that we are using to study experimentally the vortices in atomic DECs. I will discuss about the characterization we did for the vortices that we create, both in terms of the static properties, meaning the snapshots at the fixed time, and also in terms of the dynamics of a single vortices evolving within the condenser. And then I will discuss the more general context where we have more than one vortices, vortex within the condenser, and hence we have access to the vortex-vortex interaction. So the platform is an atomic DEC. In particular, we are working with sodium atoms. We are using the general recipes that are very popular nowadays in which are called gas laboratories. Typically, we start with a magneto-optic trap, which allows us to collect a few billions of atoms at a relatively low temperature, but still not sufficient to access the quantum degenerate regime. This is why then we transfer the atoms into a conservative magnetic trap, where we further cool the sample by forced evaporation. And in the end, we get we condensate with about a few million atoms with almost zero thermal fraction. Because of the geometry of the magnetic trap, in the end, the sample is elongated in a cylindrical potential, and again, it results in a cigar-shaped distribution like this, with an aspect ratio of the order of 1 to 10, and the potential overall is highly symmetric along the cylindrical direction. We have asymmetries less than 10 to the minus 4, which is something important to what I will discuss later. The detection is done by means of relatively traditional methods. Typically, we use then resonant absorption imaging. Let me tell you how it works for those that are not familiar with this. Typically, we have the sample here. We shine a laser which is resonant on an atomic transition, which means that the sample typically scatter away a radiation where it is, and hence it creates a shadow. So this shadow is then imaged on a camera, and by measuring pixel by pixel the transmission coefficient of the sample, we are able to determine the column density, which is the information that we need in order to reconstruct the atomic distribution. I have to tell you that this imaging process is fully destructive because of the atom-light interaction is somehow dissipative, and so we have a complete loss of the coherence of the condensate and also a strong heat. Okay, so overall the imaging process is destructive. And also, in order to do an accurate measurement of the absorption coefficient of the sample, we need to have some photons here behind in the shadow. So in practice, we are limited to a situation where the optical density of the sample is less than something of the order of 3-4. Okay, so this is important to know because in the end, typically the condensate is relatively dense, at least optically, that it transmits essentially zero photon in situ. So this is why we need to expand the condensate ballistically in order to reduce the column density and so allow for a quantitative measurement of the transmission of the light. So typically the sample that in situ has a cigar distribution elongated because it expands hydrodynamically. We have a faster expansion along the radial direction. So the distribution, which initially is cigar shaped, becomes a pancake. And then typically we can, for instance, do the imaging along one of the radial direction, and we get something like this. So this is the typically the image of a ground state condensate after a relatively long expansion time. Okay, so it's relatively smooth because, of course, we are dealing with a ground state sample. So how do we create vortices? During this workshop, we already heard that vortices can be created via stirring of the condensate by using spoons, but also with sticks and rakes and things like that. So there are various methods nowadays. We are using another method which does not rely on the mechanical transfer of angular momentum to the condensate. We exploit instead the Kibozurek mechanism. So probably many of you know how does it work. Actually, there are experts in this audience, and we will hear tomorrow as a talk focusing indeed on the Kibozurek mechanism. But let me remind that the basic ingredient in order to access to the Kibozurek mechanism are second order phase transition, which is crossed at the final rate. So in our case, the second order phase transition is the Bose-Einstein condensation. And typically we cool at a given rate from the normal phase to the condensed phase by playing around with the evaporation ground. So typically if you cool slowly, you have the phase transition simultaneous symmetry breaking, meaning that you fix the phase of your order parameter in the center of the trough where the density is higher, and then this information propagates within the condensate while it goes. On the other hand, if you cool fast, the spontaneous symmetry breaking happens on a local basis, so you create bubbles of orders of parameters which are somehow independent one another. And in the end, you get domains of ordered parameters which are separated by boundaries where defects may appear. So since our sample is relatively elongated, the defects appear along the axial direction, and after the ballistic expansion, these defects become visible, as you see here. So these are typical images of the atomic distribution under different conditions of evaporation. For instance, if we cool slowly, we get something smooth, so without defects. On the other hand, if you increase the cooling rate across the phase transition, defects appear with higher probability and higher average number. Actually, you can plot in this log-log scale the average counts of defect versus the quench rate, and this power law scaling reminds indeed the prediction by the Kibble-Zweig mechanism. Okay, so in order to gain a better insight into what we have here, we extended the imaging method in order to acquire pictures of the condensate simultaneously along 3 orthogonal directions. So this is the pancake after the ballistic expansion. We take then the images simultaneously on the very same example along the 2 orthogonal radial direction and 1 axial direction like this. And so here I project, I tried somehow to combine these 3 pictures on 1 single setting. So each cube corresponds to 1 single condensate. And what you notice is that when the defect is present, which actually is the vortex, you always see something. But the signature depends pretty much on the geometry and on the orientation of the vortex itself. For instance, along the axial direction, which is this square, like this square, the nodal line is always present as a stripe, as you see here. For instance, in this case, the nodal line is here. Here it is along this direction. On the diagonal, here the visibility is limited, but it is vertical, and here is on the other diagonal. On the radial direction, the signature depends pretty much of the orientation of the nodal line with respect to the imaging axis. So for instance, if the nodal line is along the imaging axis, which corresponds to this picture here, we have a signature of a kind of twist around the dip. So actually, this twist reflects pretty much the orientation of the circulation, as I will show you in a moment. On the other hand, along the orthogonal direction, we have a kind of stripe which reflects the depletion, the depletion of the nodal line, but nothing more. And of course, if the nodal line is not parallel to either the vertical or the horizontal or radial direction, you have 2 stripes. Okay, so from images like this, then we can, for instance, make a characterization of the quantitative characterization of the size of the nodal line. This is something new that was not done before. Of course, this characterization is made after a ballistic expansion, but still allows us to do a quantitative comparison of the experimental observation like this versus the Gross-Pitayevsky predictions, and this fits quite well with respect to the numerical calculations. Actually, here we have some graphs about how the nodal line is expected to expand during the ballistic expansion, and everything it works quite well. As far as the twist that was mentioned before, in order to relate this twist, whether it is an S shape, no, this is a Z shape or S shape, we made a characterization of the orientation of this twist with respect to the circulation by directly measuring the phase patterns around the vortices, doing self-hemodynamic measurements. So typically, we use, in this case, a series of Bragg pulses in order to create copies of the same condensate and interfere them. And so in the end, we get structures like this regular pattern just reflect the fact that in general, the phase of the condensate is flat, but around the vortex, because of the circulation, we get this location, which tells you exactly how the phase is winding, whether it winds clockwise or counterclockwise like here. Okay, so what do we have? So we learned so far that the vortices we have are somehow produced via stochastic method. And they are free to be along any direction in the radial plane, and we do not know a priori their position or their orientation in the lab frame. On the other hand, so these are truly three-dimensional vortices, because we don't have strong constraint about their direction and position, and it would be nice to use them in order to characterize, for instance, vortex dynamics, vortex interaction, and so on. Would be nice, but it's not possible if we consider the ordinary detection methods, because, as I told you, images like this are taken with resonant absorption imaging, which is fully destructive. And the problem is that if you want to reconstruct the dynamics, typically you need to sample the very same, somehow the dynamics of identical systems at different wave time. And of course, since the vortices are produced stochastically, you cannot take a picture of one sample and then take another subsequent picture of a different realization, because the vortex will be totally independent. So in order to push in this direction, we developed an imaging method that was pioneered by David Hall at Amherst University, which relies on the fact that typically we produce the condensate in an internal hyperframe state, which is not the one which is typically used for imaging. So typically, this state, this F=1 state, is dark to the imaging that employs this ground state level and electronically excited state above. So typically, you do optical pumping of the full population and you take your image. What we are doing instead is using microwave pulses in order to transfer a small fraction of the population from the magnetically trapped state to the bright state, right to the imaging, and leave the majority of the population in the magnetic trap. So since this state is anti-trapped, the distribution will expand in order to reduce the density and let the vortex expand, the vortex core expand itself. And so then we take a picture of this expanded cloud, leaving the atoms in the magnetic trap essentially unperturbed during the imaging. So the power of this method is that then the atoms that are in the magnetic trap continue their life, and so they can be imaged in a later moment. Actually, you can iterate this imaging method many times, like here. Here we have 7 sequences of picture that should be observed along the vertical direction. So here we have a condensate that was imaged of the order of 20 times. This was one realization, this was another realization, and so on. So we have, by combining all this picture, we have a kind of feeling of the dynamics of the defects within the sample. These pictures are actually the same as you see here. They are just squeezed along the vertical direction in order to increase the visibility of the eye. And these are nice because then, for instance, you can follow the orbit of the vortex. This is the orbit projected along the axial direction of the condensate. And from pictures like this, we can, for instance, verify some dynamics similar to what Martin was showing yesterday about his unitary gas. This is pretty much related. And actually, also in this case, vortices are expected to have orbital motion along orbits of equal constant chemical potential, the period of this orbit is essentially the same that what Martin showed yesterday. There are some small corrections that relate to the fact that we do not have a unitary Fermi gas but a Bose gas. But apart from that, it's exactly the same. So, for instance, if we take the pictures where we start with one condensate, like this. So here we have three pictures. The third one is just an extreme case of a orbit of a very small amplitude. Is a vortex in the bottom of the trap, steady. So it's pretty difficult to extract the period of frequency from this degenerate situation, but from other situations like this or this, we can extract the position of the vortex in each picture and put in the graph. We can extract the instantaneous frequency of the precession and verify without any free parameter that the frequency indeed increases during the sequence. Why does the frequency increase? This simply relates to the fact that at each time we are extracting a few percent of the population, so the chemical potential here goes down, and so the period as well. So the chirp that we are observing here in the frequency relates simply to the fact that we are depleting the condensate in time in order to allow for this iterated imaging. Yes. Okay, so now the point is that we know that we can follow the dynamic of individual vortices. It would be nice to extend this method in order to study the interaction of vortices, because we realize here a platform where we can follow full 3D vortices. And in 3 dimensions, of course, the interaction, the situations, the possibilities are very rich. For instance, we can consider a situation of vortex annihilation, vortex decay, and vortex reconnection. For instance, when we launch vortices with orthogonal directions, like a situation like this. Reconnections were studied in various contexts. For instance, here we had some results that were presented almost 30 years ago in liquid crystals. In the superfluid reconnections were observed on liquid helium by means of tracer particles. In this case, reconnections are clearly observable, as you can see here. For instance, here we have a line which breaks in two. It's very powerful, but on the other hand, since the tracer particles here are very large with respect to the size of the core of the vortex, it's difficult to use to access to the reconnection dynamics at the macroscopic scale. On the other hand, here we have access directly to the core size. So in principle, it could be important and effective to extend the method and study the reconnection closer in details. What do we have in the lab so far? What we observed is that in some cases, the vortices do not interact where they approach one another. For instance, in this case, you see that the sinusoidal orbit of one vortex is unaffected where it crosses the orbit of another one. In other cases, like here, instead we have a strong interaction where the orbit cross one another. In particular, here we have a strong change of the visibility of the contrast, and also if you fit arc of sinusoidal, you would observe that here there is a kind of phase delay. In other situations, like this one here, we simply lose both vortices at the crossing. So there are signatures of a very strong interaction. On the other hand, pictures like this are not very helpful because, as you see, the signal to noise is relatively weak, and also we are missing important information, such as, for instance, the relative orientation of the vortices, which is, of course, essential in order to quantify and characterize the interactions between vortices. This is the reason why we developed a different approach to the imaging, which relies on a two-photon transition to extract the atoms to be imaged. Don't want to be too technical, but let me know simply that now this approach allows to go through Zeeman levels that are insensitive to the first order to magnetic field gradients. This is important because the dynamics of the expanding cloud to be imaged happens within the magnetic field gradient of the trap. And of course, these are very strong. So we prefer to be magnetically insensitive. So we use this MZ equals 0 states. And also this extraction procedure allows for, with this method, there is a direct one-to-one relation between the position of the extracted atoms and the frequency that we use to that we apply. So the idea then is that because of the magnetic field gradients and the presence of the Earth gravity field, we have the possibility to choose the height of the extracted field simply by changing the frequency of this radio frequency so that for instance, if we apply a chirp to the radio frequency, we are able to introduce extracting front from the condensate that can be tuned in order to obtain a signal that somehow tell us both the position of the vortex and its orientation. So it's a bit complicated, but the crucial point is that if we move this extracting front at a velocity that corresponds to the velocity of free-falling atoms, the extraction happens to contain the information about the circulation that we have here. So for instance, if the vortex is pointing outside of the board, we would expect a kind of dispersive signal with a negative slope here. On the other hand, if the vortex rotates in the other direction, the slope would be opposite. I don't have the time to tell you more in detail things, but actually you can do a thorough simulation of the extraction procedure, and in the end, it is indeed like that. For instance, this is the case of a vortex rotating counterclockwise. You get a signal like this. On the other hand, if the vortex is along the vertical direction, you would expect a symmetric signal like this. Okay, so this is about the general ideas. How do we apply them? So here we have 3 pictures of the very same condensate taken at different moments. In practice, what we do is taking these pictures, we then calculate the residual with respect to a Thomas Fermi profile. We integrate along the column, and in the end, we get signals like this. So here you clearly see this dispersive signal, which corresponds to this defect. And if you introduce a color map like this, and use this vector as a column in this matrix here, you pile up the various vector, and in the end you have a kind of film of the vortex, which is moving along the axial direction. So in time, this is time, and this is the axial direction of the vortex. So here we see that the vortex is slowly processing from negative x to positive x, and at the same time it is rotating like a spinning top, okay, slowly rotating. So this vector here corresponds to this, and this one here corresponds to this, and so on. And in general, for every realization of condensate, we get pictures of fields like this, which are composed of about 80 different extractions. So you may wonder, how is it possible that the vortex does this kind of, precession, because we know that I told you that the potential is highly symmetric along the axial direction. So if the vortex lies within a radial plane, there would be no need for the vortex to precess in the radial plane. But on the other hand, if you allow the vortex to tilt out of the radial plane, you would have you expect an increase of the energy, which actually results in a torque, which indeed induces the precession of the nodal line. So actually, the information about the speed at which this spinning happens tells you exactly what is the tilt angle out of the radial plane. We can somehow calibrate this, but this is not so important. So let me move to the measurement we did on interacting vortices. So what was done so far? So far, with ultra-cold gases, the interaction among vortices was studied essentially in the context of condensate stirred, 3D condensate which were stirred, whereby many vortices were produced, all aligned one another. And so the strong interaction among these polarized vortices result in because of lattices. Of course, this is very interesting, but relates essentially to a two-dimensional interaction. Okay, it's like a Coulombic interaction, repulsive interaction among vortices. In other experiments, like the one that were discussed on Monday, the effective two-dimensionality of the system resulted in interaction among vortices essentially of 2D nature, while on the other, when we are focused more in the context of the 3D interaction, where, for instance, one should expect to have a reconnection. For instance, in a situation where we launch vortices with orthogonal direction. The idea is that as long as the vortex have relative distance larger than the radial Thomas Fermi radius, we expect that the orbit is unaffected by the presence of the second vortex. On the other hand, the interaction among vortices should become stronger at shorter distance. So what are the observables we have available? Essentially, our observables relate to the position of the vortices versus time. So this tells us, of course, where the vortices are, and also which is their absolute velocity and their relative velocity. Another observable relates to the rotation. For instance, if we observe, like here, color sequences of the same time, like green, red, this means that the vortices are somehow oriented in the same direction. While in other situation, like here we have a color sequence, green, red, green. This means that the vortices are oriented the opposite way. Another observable which we have available is the visibility. So for instance, in this situation here, we see that the visibility of the vortex does not change after the interaction. So let's say that the vortex interact when they come close one another. In this case, the visibility does not change In other situation like this or this, the situation change, the visibility changes a lot. And this, of course, is very important in order to understand what's going on. So we can, in principle, classify the interaction against, for instance, the relative orientation of vortices. Let me mention that all this kind of simulation were done by Luca Galantucci and Carlo Barelli. So let's consider, for instance, the situation where we have vortices aligned in the same way and orbiting on different orbit parameters. So in this case, both numerically and experimentally, we see that indeed the vortices, the interactions remain very weak. On the other hand, if we start from with vortices with orthogonal direction, the outcome of the interaction does depend pretty much on the relative velocity of the vortices when they approach. The relative velocity is directly related to the orbit parameter. So if, for instance, we start with vortices that are pretty close one another, the relative velocity at the when approaching will be small. And actually, in this case, because of the small velocity of approach, the vortices will tend to anti-align, and so because of the various effects, including the effects of image charges outside of the condensate, the vortices, instead of reconnect, will somehow rebound and without any reconnection. On the other hand, if the relative velocity increases, we will have more complicated situation where reconnection can happen, for instance, like here, once or twice. From the experimental point of view, what do we have? As far as the rebounds, we observe that indeed these processes may happen, but essentially when the relative velocity is extremely low. For instance, here I plotted the full set of realization that we have, and we noticed that the rebound happened with unitary probability at extremely low relative velocity, and then the probability of having rebounds drops very fast when we increase the relative velocity. And also the probability of having a rebound depends also on the relative orientation of the vortices. If we start with vortices of opposite orientation, the probability is in general higher, as one expects also from numerical simulations. If we increase the relative velocity, actually we don't increase the relative velocity, we just post-select images that relate to vortices that move with higher velocity. Then we observe that reconnection should take place. This is a general observation from the numerical simulation. From the experimental images, we don't have a clear evidence of the reconnection so far, because actually we don't have yet enough resolution, both spatial resolution and temporal resolution, to observe directly what happens at short ranges. But on the other hand, we observe that in cases like this, the dynamics is heavily modified by the interaction. So in particular, we do observe very often losses of vortices, which is pretty probably related to the fact that we have reconnections that take place next to the edge of the condensate. So this means that starting from two vortices of about the same length, because of the reconnection, we create nodal lines, one which carries essentially the full amount of energy and circulation, and a small piece which is just not observed because it contains a small amount of atoms, and this the visibility of that becomes below our threshold. And so with that, I think that I'm running out of time. See? Yes. Yes. So this is just to conclude, is a study that we made about this ejection mechanism, where indeed we observe the loss of one of the two vortices. So numerical simulations show indeed that if the reconnection happens next to the border, to the edge of the condensate, then we create a small nodal line that travels then at a very high speed, so of the order of speed of sound, and typically another part of another nodal line which carries essentially the full initial circulation. And actually, this kind of events happens when the orbit parameter of at least one of the two vortices is pretty high, and so this is confirmed also from this statistical analysis of the defects. So this brings me to the conclusion. So I told you about the general context of we are considering about with the production and characterization and the study of the dynamics of vortices. What we are focusing now relates to a problem that is somehow left in the drawer, and relates to the fact that when we do our Kibbles generation of vortices, we notice that at fast quenches, we have a kind of saturation in the number of vortices, which relates probably to the fact that we have a strong and fast coarse graining dynamics that is somehow hidden in the early time of the history of our condensate. And we are going to extend our imaging method in order to study this dynamics of the vortex in the early times, where probably we had some kind of turbulent regime in the condensate. Yes. Thank you for the attention.
All right, let's take questions.
Could you look at collisions between two vortex rings?
This is something that we are considering with Carlo and Luca. Yes, but yet we don't have results on that.
How would you produce it?
This is something that we have to demonstrate yet.
Go ahead.
I was wondering, could you extend your movie technique to also again 3D, like look at the 3 projections again, probably by, I guess, changing polarizations quickly so that you get a nice 3D tomographic image.
The problem is that it's not a tomographic imaging that we are doing. What we are doing is like cutting a slice of a salami. So this slice is cut, and at the same time it folds down and interfere with itself. So, for instance, if you look along the axial direction, you cannot see the nodal line as you would see with the previous original resonant imaging. Yes.
Any other question? Actually, I guess so they're pretty intrigued by the CW thing here. So you were saying earlier that it's about 4% of the atoms each image. I guess it must be.
Yeah. So actually, at the
less than that.
At the very beginning, we were extracting yes 4% of the population. The second approach allows us to reduce the amount of extracted atom to about 1% of the population. I think that there is margin to go further down with the extracted fraction, both in terms of efficiency of the imaging and also in terms of overall atom number at the very beginning. Probably we can improve slightly on both sides.
All right, one last question.
Do you ever see higher charged vortices in your cable direct technique?
No.
Of production?
The problem is that we can observe the vortices only after a relatively long equilibration time, where, for instance, the thermal fraction is completely gone. And so it is very likely that during this equilibration time, the highly charged vortex will lapse.
All right, let's thank the speaker again. We'll have a color break.